technique, not only to data, to process, to different aspects that we can find in the domain of computer science. And semantic mining tries to mix a specific aspect around the web. That is the main aspect. And semantic mining is in one domain where we try to exploit the semantic web, try to find, to extract knowledge. That's the idea with semantic mining. That means there are different techniques inside of semantic mining to try to exploit this knowledge that is available in the web. Text mining is a technique that belongs to other domains, but now we use in semantic mining, and there are other more specific to the web. And in our case, we work in this specific domain. We have worked in this domain. In general, semantic mining tries to use these different sources of information that we have available in order to build knowledge to different types of applications in different domains. But one of the first problems is that we have a lot of mining techniques, data mining, semantic mining, etc. And we have developed in our group different methodology, and one of them is to try to use this mining technique in one correct way when we have in one organization. And the idea with this methodology is to try to use this different technique, that means data mining technique or semantic mining, together when we have one specific problem. And that is the idea with this methodology. This methodology tries to take in account different aspects that normally we don't use or we don't consider when we have a problem. And the idea with this one is that we're going to try to specify data analysis tasks, and the data analysis tasks use the different mining techniques. But the main aspect with this methodology is to define the data analysis task that we need in a given moment to solve one specific problem. For this case, the methodology proposed 3 phases, and in each phase we have one specific goal. In the first phase, we try to know the organization, and we use tools from the business intelligence paradigm. In the other phase, we try to prepare the data, because that is one of the main aspects. If we don't have a good data, we are going to have a very bad data analysis task. And this phase is only for this specific aspect. And the last one is used to develop the different data analysis tasks. But here we introduce one concept, and it's the idea that we need to work with different data analysis tasks when we have a given problem. And we call that one autonomic cycle of data analysis tasks. The methodology has different aspects. That means we define the process and the future scenario where we like this specific, when we like to introduce the specific data analysis task, and it's inside of this future scenario where we are going to define the cycle, the autonomic cycle of data analysis tasks. We can have a lot of future scenario in a way to build different specific autonomic cycle of data analysis tasks. And for each one, we describe this specific autonomic cycle. The other aspect is that in each data analysis, in each autonomic cycle of data analysis task, we need to specify the specific data model that we're going to use. And we propose here 2 concepts. We use 2 concepts. The conceptual view, that means is where we describe the variable from the organization or the external source and the operational view. And with this one, we describe the multidimensional data model that we're going to need and the specific task to extract and to load the data in the operational data warehouse where we're going to have the information. In this case, with this type of thing, we use the data science paradigm. And the last one is to specify the yeah. In this, for this one, we use different tools that allow specify, for example, the extraction, transformation, and load operation, or the curation, in this case, the aggregation of the data from the external view. For all of them tasks, we can have tools to help in the design and in the when we try to operate, to define the operation, to prepare the data warehouse for the different data analysis tasks defined in the autonomic cycle. And in this last step is where we develop and we define the technological aspect to develop the autonomic cycle. And in this case, we use normally this one, but we can use for each specific autonomic, for each specific data analysis task, we can use different type of data mining technology. We use particularly this one. We have developed a lot of autonomic sites. For example, this project, this is a project that has 3 years. We have developed more or less 7 autonomic sites for a specific goal in the smart classroom. For example, the first one is to determine in real time the current learning paradigm that the student use in the smart classroom. In this case, the different data analysis tasks are dedicated to determine the current learning paradigm to adapt the smart classroom. That's one of the examples. And we have all in the same smart classroom. We have other autonomic sites for different things, for different goals. For example, this is the autonomic site in the case of the first to determine the learning paradigm of the student. And here we have different types of data analysis tasks. We have, for example, one to observe the smart classroom, other tasks to interpret the information, the situation that we have in the learning process, and some of the data analysis tasks is to make decisions in the smart classroom. That is the cycle. And here we have, for each one, we can use different mining technique. For example, here, this is, in this case, this is a classical data mining technique that we use. In this case, we use graph mining technique. That means we can mix the different mining technique and they work together in order to supervise the learning process. That is the idea. And this autonomic site have, look at here, the different technique that we use for the different data analysis tasks, and they work together in order to supervise the learning process. That's the idea. Okay?
How do you know that you're choosing the right areas?
Normally, for each one, remember that they are data analysis tasks that use a specific mining technique. And we can have measure to determine the quality of each one. we can use performance metric to determine the quality of each one. And in the case of the smart classroom, we have educational metric from the specialist of the domain that determine that if the behavior of the learning process is correct with respect to the student, with respect to the course, etc. That means we have two types of metric. The metric for each data analysis task, or in this case, learning analysis task, and the metric of the all of the process with respect to the autonomic cycle that we propose, the goal that we like to reach. Okay, in this case, we have two types of metric that we can consider for this type of thing.
So there is very tight relationship between this autonomic cycle and the learning system.
Yeah.
Because you have to plug it at the first step line.
Of course, we are
multiple plugs.
Yeah, we need. They need to work together.
Yeah,
they need to work together. They need to work together. Okay. We have applied.
It's something that should be co-designed with. So when we design the learning system, then we design at the same time the autonomic cycle. Or is it possible? Or is it possible to implement it to add this system on top of existing learning system?
Yeah, normally we can use the learning analysis task alone, all together. That is the main point, because that we can see that like a service. And in our smart classroom, we model the different components of the smart classroom like agent. And the agent has this type of service in a given moment. And they work together, but we can call the autonomic cycle. The autonomic cycle can work alone, but the agent can call one of them if they need in a given moment to make decision. Okay? That means we have two points of view in this case. But the idea of the autonomic cycle that the autonomic cycle works to supervise the process where that we like to study. Okay, and we have
kind of monitoring.
Yeah, it's one smart supervision. We have applied the same idea in this context in the oil process. For example, for the production, it's one smart supervision of the oil process in a given moment. We have applied the same idea to study the communication network, and now we develop in the smart city we develop the same idea. For example, when we like to control the transportation system, one specific aspect, we work in this type of thing at this moment. Okay, we have applied the same idea. In this case, we have different types of mining technique working together using data from the organization and external data of the process. We can mix this type of information to supervise one specific process. That is the idea.
Do you need to revise something in your process? Do you have to start over, or you can?
No, yeah, that's a good question. Normally, because we try to use real data, and sometimes we need to there are sometimes models that with the new data we need to update the model. In this case, we need to go only to the specific task that use this specific model and relearn the model or rebuild the model in order to have one model that follows the process that we like to study. But
how do you know that it's not affecting the other?
Because we have one degradation in the metric, for example. That depends on the process. For example, in the oil process, we know that we have some models that need to follow the real process, and when we have a difference between the real model and and the model that we have learned, at this moment we know that this model needs to be revealed. That means we need to have, we need to include the new data, because maybe the model has problems to follow the real process. That is the type of thing, but we use the metric to do that, to know when we have this type of problem. And in other case, we can have online learning process. That means the model can, that is the type of stuff that we can, that the learning mechanism can solve it with the problem. But that's the point of the problem. If we have online learning of offline learning, that depends on the type of problem. But in some cases, of course, we need to go directly to a specific data analysis task, where if we don't have one of online learning, we need to include the new data, etc. Okay?
In this type of supervision, we use a tool for decision making to improve the process. I'm just wondering where the decision making is done. Is it done local at the edge, at the central point, or somewhere in the front? Like,
yeah, and that's the point. For example, in the case of a smart classroom, what type of the decision that we can make is, for example, define the educational resource that we are going to use. Okay, the educational resource that is going to use the virtual learning environment. That is the type of decision that one smart classroom can take with a problem.
For example, for its communication network, the decision is made locally, one part of the network is to identify that there is an issue and try to solve it locally. Or
no, maybe for example,
supervision and then,
or maybe for the quality of service. No, what type of decision is to the quality of service, to define the priority between the different type of flow that we have in the moment. That is one type of decision that we can make, to define this priority between the flow. Okay? That means normally the decisions are the decisions that we can take, that the autonomic cycle can take according to the goal that the autonomic cycle like to reach. That's the idea. Okay? Okay. In other domain where we have one of the first world is at the level of semantic mining. In this case, the idea with semantic mining is that we are going to mix the web mining technique with the semantic web, and we have in this case different sources to exploit, and we have different type of technique in the web meaning. When we talk about web meaning, we have different techniques that we can exploit. One example of the thing that we have, look at here, and in each case we exploit different mining techniques. In this case, I'm going to explain you one example where we mix different techniques to interpret a Spanish query. A Spanish query on the web. Okay. The idea is that we are going to Spanish query. That means we have one. We can propose in natural language, in Spanish, query on the web, and the idea is to try to recover information from the web according to this information. And the idea, in this framework, we have developed a framework with a lot of ontology to try to understand the query and to search the relevant information. We have different types of ontology. We have one ontology to guide the process, okay, to interpret the query, and we have a specific ontology to the different tasks and for the information that we need to keep. That's the idea. I have some slides in Spanish. And the first one, the idea with the task ontology is that the task ontology is going to integrate the different components of our framework, and this ontology is going to guide the process to understand the Spanish query. Here we have a general view of the task ontology, and here we have the invocation of the different component, okay, of the different component of the framework that we have developed. That means the task ontology call the rest of the ontology in our framework, and using this ontology, when we receive the query, we start the different steps to analyze the query using the rest of the component. The task ontology calls the rest of the ontology to solve the different aspects that we need to consider to interpret, in this case, the Spanish query. For example, the first step is the morphological lexicon analysis. In this case, we use these two ontologies. For each ontology, we stamp the specific part of the ontology. This is one example of the lexicon ontology to describe the information in Spanish, to interpret each sentence. And this is an example of the onomasticon to define the different thing, the different substantive that we have in our framework. And then we have to step to interpret the sentence, to classical step, the syntactic semantic analyze, and for this case we use the linguistic ontology. The linguistic ontology describes the grammatical aspect of the Spanish language. In this case, we are going to use this ontology. We call this ontology for the syntactic and the semantic analysis, and we have a specific role for each case. And the last step is the pragmatic analysis, and in this case we have another ontology defined by two types by two classes. The entity, to define the entity, and to define the event. The event are the event, are the verb, okay, and the entity are the different thing, the different substantive that we have in our ontology. And this different entity, the relationship between these different entity is by the event. It's defined. This definition of these two classes is one standard definition for this type of ontology, okay? And this is an example of the view of this ontology, and with this one we can do the pragmatic analysis, okay? And now when we have the stance of the query in our ontology, we can transform this ontology in different things. We can transform this one like a classical, we can transform this one like a ontology, or we can define one SQL query, or in our case we define Boolean expression to go to one internet engine, for example Google, Yahoo, etc., to try to recover information from the interpretation. Remember that this is the result of the interpretation of the Spanish query, okay, using our ontology. Okay, and this is one example of the transformation in one Spark query, okay. Okay, what is the idea? Now, when we can you?
How did you map between the linguistic
No, all of the how ontology is from the framework. That means the task ontology link the different ontology. The task ontology called the linguist ontology, the interpretative ontology, in order to do the different analysis. It's the task ontology that link the different. But these ontology are for how framework. That means we have to find the different ontologies for how framework. That means we know that we don't need to map the linguistic ontology with the rest ontology, because we know that the class, etc., we have defined the different ontology with the onomasticon ontology, the lexicon ontology with the same class to avoid that inconsistency, for example, between the ontologies. We don't need one alignment between the ontology because we have defined the different concepts with the same norm, the same name, the same property, etc. Yeah. Okay. Okay. The other aspect that now we are going to have a lot of recovery documents, and how framework needs. Yeah, at the end of the analysis, we can have different things. For example, one of them is that. That means we can, with this interpretation of the query, we can build one query. Two how ontology. But one of the main points, let me go here. We can build that. Okay, and go, for example, to Google and to recover a lot of information. Okay, with the same query that we have interpreted, we can build a query and go to one specific internet engine, for example, to Google. But we are going to recover a lot of information, and how framework need to interpret this information, and to do that we use to measure. Okay, we are going to describe the query and the different documents that we have recovered using a vector model. That means we have the set of words that describe the query and the document, and with this information we are going to calculate this value at this value. That's the idea. And with this value we can determine, with this value we can determine the relationship between the query that we have interpreted and the information that we have recovered. The information that we have recovered, remember, that is this one. Okay? And the idea with this one is that we are going to try to determine, we can rank now this information in order to determine the relationship between the query that we have interpreted with respect to the information that we have recorded. We can rank this information. That is the main point. And we can do another thing. This is a general information about the tool that we have used. But the main point here is that with this information that we have recovered, we can learn. That is the main point. We can learn. What is the way to work? Okay, we can learn from the knowledge term that we have in the query. Remember that we have a lexicon, an onomasticon, Maybe we can learn some information new in the query, or we can learn from the recovery document. And that is very, very interesting. Okay, in the first case, for the knowledge term, we can do a morphosyntactic learning. In this case, we try to study the component of the word in order to know if one is the word, the term is a verb, one adjective, one adverb, or we can use vocabulary. We can use vocabulary to learn different type of vocabulary to learn. That means in this case we can use different way to try to learn a term. And the idea to learn the term is to include a new instance in the lexicon or onomasticon, okay? But in the other case, well, that is an example of the algorithm that we have developed in order to learn new term, new verb, new verb, and this is more or less the result that we have obtained. But for us, the other aspect that is very interesting is to learn from this source, because we are going to have a lot of new information from the different documents that we have recovered. And in this case, we have one procedure to learn that is based in the relevant entity and the relevant verb. And we use more or less the same idea to determine the relevant document. Remember that I have told you that we can rank the relevant document, and we use the same idea, the same metric to determine the relevant entity and the relevant verb. And we have a new ontology where this relevant information where we are going to store this new information, and we can use this new ontology for different things. That's the idea of relevant entity and verb. That means relationship is defined using this metric. Remember that this metric is the same that I have presented previously, and is a way to define from the candidate. Remember that the different document has different candidates. We need to select the best one, and with this metric we can do that. And with this information we can feed the learning graph.
So, can you provide just one slide, please? Yeah, your FI here. What is
This one?
Yeah, it's process test.
Yeah, because remember that the process tests are the document that we have recovered, but the document that we have in the first position in the ranking that we have done previously. And in this case, we analyze the content of the test. We analyze the content of the test to determine the priority of this test, the priority of the information that we have in the test. And we select two types of information, the entity and the event. That means the verb and the entity that we have in this verb. And they are going to be the candidate, and we are going to calculate this one for the set of candidates that we have.
My problem is that I don't understand how you're computing your idea, because it's the inverse document frequency, which means that you assume that you have the whole set of your documents.
We assume that we have different texts, ranking according to the relevance to the query that we have previously recovered, and now we study the content of each document or each link and inside of them we try to determine the candidate to be one entity or one relationship to the learning graph. And the idea is here that we use each term that represents one substantive, etc., in order to determine if this term can be a candidate to go to the learning graph.
Yeah, that's right. If the same term is present in all the documents, you don't need it.
Yeah, that's the reason that we use. Remember that this one determine the frequency of the given term in the different document, and this one determine if this term is discriminant. It's discriminant because maybe, for example, we can have one term only in few documents, but it's very important. And maybe this one is not frequent, but it's very important. That means we combine here two aspects: the frequency of the term in the different document, and if this term is very discriminant or not. We need these two metrics in order to have a very good entity and a very good relationship. That's the reason that we have two goals in this metric. Okay? Okay, in this way we are going to have a learning graph with the different entities and relationship between these entities. Here you have different view of the class and the relationship that we can obtain, and with the learning graph we can do different things. One of the things that we can do is to update the lexicon and onomasticon and the interpretative ontology. That is one of the things that we can do. And other thing that we can do with the semantic, remember here we had the similarity between the link and the query, and according to this one of the things that we can do, now we can have one domain ontology according to the query that we have to. That we can build. We can build now with the entity and relationship, the relevant entity and relationship. We can define domain ontology. We can define taxonomy. We can define electronic lexicon using the learning graph. This is the example of the domain ontology from the query, using the query according to the query and using the document that we have recovered. And this is an example of the electronic lexicon of noun and verb, and this is one example. We have developed like this tool like a service, and we can use the same idea of the learning graph in order to analyze documents. And with this type of thing, we can, for example, build abstract from a set of documents, for example. That's the thing with the learning graph that we can do. We can use that like a service for different things. That means it's not only for the framework that we have developed. We can build the taxonomy. That means we can take the different sentence in one text, and according to the sentence, we are going to try to find we are going to try to find this relationship is A in order to build a taxonomy. That is one of the things that we can do with the learning graph. Okay, I know that I have I don't know, not worry. Okay, in the other domain that we have several work is at the level of ontology mining. Okay, at the level of ontology mining, we have developed in different. When we talk about ontology mining, there are different things that we can do. One of them is at the level of integration of ontology. And at the level of integration of ontology, we have different things that we can do. And we have worked in different, in each of them. I'm going to present some of the work that we have in there. At the level of the alignment, one of the alignment is to determine the relationship between concepts. At the level of the relation between the concept of different ontologies, okay? And normally the idea is that we are going to obtain one table with this relationship, and we are going to use one similarity function in order to determine that. And in the literature there are a lot of similarity functions to determine that. That's one of the problems. We don't know for one specific problem what alignment technique to use. That is one of the problems, because there are a lot of in the literature using different approaches. Okay, there are linguistic approach and structural approach. Okay, and in each one there are different. In each one there are different point of view to try to solve this problem. For example, here we have the case when we try to mix, because we can to mix the different similarity functions according to the problem that we like to attack. That means we can use one linguistic approach with one structural approach. One of the work that we have developed is to try to select to try to define one algorithm to select in a given situation what is the alignment technique to use. Okay, is the algorithm that is going to try to define that, because we have a lot of them, and we have used in this case the ABC algorithm. The ABC algorithm is a very known algorithm used in the people that work in the domain of optimization problem that have used this technique, and it's based in BIF, scope BIF, and employer BIF. And the idea is that the scope BIF search food source and propose this food source to the rest of the BIF in order to determine which one is the best source. That is the idea. And in our case, we use the same idea, but now we are going to have a scope BIF that try to study different alignment technique in a given moment. And according to the quality of the alignment technique, each BIF is going to try to propose this alignment technique to the rest of the employer BIF. That is the main idea with this algorithm. We have, we need in this case define the quality of the alignment technique, and we have defined the quality according to two criteria. One, to define the number of nodes that we can align with the technique, and the other one, yeah, times pi, and the other one is based on
people who had the time constraints.
Okay.
So
and the other element that we consider is the execution time of the alignment technique. Using these two criteria, we can define the quality of each alignment technique. And using this idea, we have tested different alignment technique in different benchmarks. We have used different ontology benchmark in order to try to use our technique. And for example, here we have some example of the quality of the selection that our algorithm can do. For example, here our algorithm proposed to use the E and F technique. That means propose to use the E and F technique. The E and F technique, that means propose to use this technique. But for this other ontology, propose other technique. Okay, that means here we can see that the different alignment technique has different behavior according to the ontology that we need to align, and how algorithm can determine the best alignment technique. Other aspect when we carry out ontology mining is to try to link ontologies. That means we need to try to find the relationship between the alignment determine the concept. But if we like to navigate between different ontologies, we need this type of technique to determine this bridge between the ontology. And we can determine this bridge using the identical concept, but when we don't have that, we need to create a meta-ontology, like a bridge. We have one word around this idea. The way to create this meta-ontology. And in this case, we have defined different concepts. One of them is, for example, in our case, what is the way to define the similarity between concepts? And we define the similarity between concepts according to the property that they share. Okay? That's the idea. And our meta-ontology is composed by the meta-concept defined during our algorithm. Okay? For that, we are going to use different data structure. We are going to have, in this case, we are going to have the idea with the meta-ontology is that we are going to have concepts that we can align, but there are other concepts that we cannot align, but that is a new information that we need to keep. The other aspect is that now we can define group of concepts according to the property that they share, and that is very important. That means now we are going to group the concept according to the property that they have in common.
I'm sorry to interrupt, just a question about the similarity measure. When you measure the intersection on the union of all attributes, how do you precise the threshold that decides if they're similar or not?
In this case, the threshold, I'm going to talk about that, okay, because that is a measure that we can adapt, okay? This limit is something that we can determine according to the problem that we study, okay? Okay, according to the definition that we have, the other aspect that is very important is the category. We are going to define a category with the set of concepts that have the same property. We can define a set of property, and with this set of property, the set of concepts that share this property that belong to one specific category. And we are going to have this type of relationship where we have here this concept is the domain, and this concept is the rank, and in this way we can have defined the scope of one category, and we can define the rank of one category. And the other aspect that's very important is that now when we have defined one category, we can define the subcategory. That means one category that is included in another category. Okay? We can have generic subcategory and a specific subcategory. One generic category includes several subcategories. And one specific category is one very special category. And we can order the different subcategory for a given set of context. Remember that the context is a set of ontology that we are going to use to define the meta-ontology. This order can be defined now between the subcategories. With this idea, we can develop one algorithm where we define the subcategory, we determine the order between this category, and we are going to use the generic subcategory to try to define the meta concept. Okay, this subcategory are being the candidate, and with this subcategory, we are going to try to determine the subclass relationship between the subcategory. In this way, we are going to know the meta concept and the relationship between the meta concept. With other aspect that is very important when we develop one a meta ontology is to define the metric to know if the ontology is okay or not. Remember that we use a set of ontology, and now we need to know if for this set of ontology the meta-ontology is correct or not. And we can use different metrics. For example, robustness to define if the meta concept includes the concept of each ontology, or the completeness to determine if each concept is included in the different meta concept of the meta ontology, and the precision in order to determine the number of meta concepts that are used to determine if one concept is included in this one. And according to this metric, now we can use one algorithm like our algorithm. Here, look at that we have three ontology, and the idea is to try to define a meta-ontology using these three ontologies. We start with one of them that we define the sub-ontology, and according to our algorithm now, we need to determine the concept that we can align. In this case, these concepts are very important because now they are the first candidate to define a meta concept. But here we have a new concept that we need to study. And here we have the different category, the initial category to define the meta concept. And with initial category, we start to study if here we have the different definition for this example, but the main point here is to study the relationship between the category in our context and the order of this subcategory in order to determine the generic subcategory. And with the generic subcategory, now we can try to define this relationship in order to determine the meta concept that we can have in this set of ontology. And in order to do that, in our case, we have defined the different subcategories, the order within them, and they are going to be the meta concept for this set of ontology that we have at the beginning. And here we have one example of the metric to define the quality of the meta ontology that we have generated. In this case, the threshold is one parameter that we enable the similarity between the concept that we can customize according to this quality that we like to obtain in a given moment. But this is the final meta concept that describes the information from this set of ontology that we have. That means this is the meta-ontology that we have generated at the end of the day. Other aspect that is very important at the level of ontology is the fusion between the ontology. That means when we need to have a big ontology with different ontologies, okay? And normally the technique that we find use one original ontology and try to enrich this ontology. We have developed one method based on this idea, because normally in this case sometimes there are information to the other ontology that is not included in the final result, and we have developed one algorithm that tries to solve this type of problem. This is the classical case. We part from the concept that has been aligned, and we include this information. Okay, we include the information of the concept that have aligned in the final result. Okay, the concept has been this one. We include this one in the final result. That is the classical merge algorithm that we find in the literature. But look at here that we have included this information, but this information is wrong. Okay? The idea, we have developed one algorithm where we try to include all of the information. That means we are going to have one ontology with the information of in this case, of the two ontology. And in this case, we had different situations. We had one situation where maybe the information that we have partial aligned node that have been partial node that have been aligned, and we can include this information directly, but we need to determine the relationship for the rest of the information that we cannot include due to the align of the node. And this is the thing that we try to do in each case. And we have different situations. Sometimes it's the ancestor that we don't have. Sometimes if with the descendant we have no problem, that we can include. Normally it's that that algorithm can do. But one of the problems is when with the ancestor we can not include. And the case, the very hard is when we can align only the node that we have in the leaf. In this case, we need to include the rest of the ancestor. That means, in this case, we need to include. No, it's not this case. In this case, we need to include, for example, here where we align only these two nodes, we need to include the rest of this information. And we need to determine this relationship. In this case, we use several graph relationships to keep the relationship between the ancestor of this side with respect to the relationship that we have in the other ontology. Okay, that means here we apply some type of graph mining to try to solve this problem. The other thing that we can work is when we can, typically when we combine one ontology, we combine this ontology with another ontology. But in some kinds, we need to combine this ontology with different ontology. That means we need multiple alignment of concepts. For example, here, this is the source ontology, and we have different ontology. And we need to enrich this ontology with different ontology.
So the first one is some kind of pivot.
Yeah, it's the source. Yeah, it's the source that we like to enrich. Okay, and the classical algorithm use attack this problem only. Okay. In this case, that means we are going to try to define the alignment between each concept from the between the source ontology and the reference ontology. That's the idea, and to find the best alignment at the level of the concept of each concept using one similarity measure. The main point here is that we are going to have a very complex graph to describe that. Okay, and we have used some idea to try to solve this problem. We have used one similarity function that consider different aspects. That means consider the similarity between the sibling, the descendant and the ascendant. But the main point here is that for in each node here, in each node, to decide where to go, we are going to use two metrics. One metric that defines the probability to go to one of the path and or to one of the arc, and this one is based in the similarity function between the concept, and the other part is defined in this notion of pheromone. Okay, and the pheromone in this case is defined according to the quality of the path that we have found. We are going to date the pheromone in each iteration. This is like a reinforcement learning that we apply here, because this measure is defined according to the number of nodes that we can align in the path. Okay, but the number of alignment that we are going to have is according to the children, ancestor, and sibling that we have aligned. According to this one, we are going to have a set of alignment. We are going to define the space. We are going to calculate the similarity between the different concepts, and we are going to have now a solution that is defined by the path that we have, the best path that we have found in a given method. Okay, that is one type of thing that we can do at this level. I think that I have no more time, but only I'm going to talk about one of the things that at this moment we go. I'm going to go to the last slide to talk about that. In graph mining, we have the different work. In this case, the idea is to use the different metrics that we have in the graph in order to find information that can be useful in a given context. And this is the type of metric that we can have. We have different types of metric, and using this type of information, we can here detect a specific node that we can enrich. And this is the type of thing that we have done with this type of algorithm, using different types of metric from the graph mining, from the graph theory, in order to enrich this type of graph. But at this moment, we work in this domain. We try to use this information to extract knowledge. Okay, that's the idea. And we are going to skip different slides. I'm going to go to the last one to try to. That is very important. That means now, with this type of information, we can start a lot of things. We work in 4 specific aspects. The first one is to try to define trained data. Trained data in order to build a specific knowledge model to classify, to look. That means the idea is to define role, associative role. That is the idea is to use the linked data to build training data that can be used for different machine learning techniques. That is one of the things that we try to do at this moment. The other aspect that we can do very easy is to enrich other ontology using linked data. Okay, we can improve ontology using linked data. That is more it's more automatic with the tool that we have. The other aspect is that normally the current semantic web is based in descriptive logic, and the engine that we use, the different tool that we use, is based in descriptive logic. But inside of the web, there are other type of situations that we cannot describe with descriptive logic. And we work in one project that we try to combine this other type of logic that we call dialectic logic. I'm going to talk about that in another slide. And the last project where we are is to try to define machine learning technique using linked data. We have a previous work where we have defined, using ontology, we have defined the system tree and Bayesian network. Okay? The idea is the same idea, but now using linked data to build this type of machine learning technique. To exploit this information in order to define different machine learning technique. Okay, at the level of at this level, the idea is that we need this. These are examples of the sentence that we cannot describe with descriptive logic. We need other logic. And the dialectic logic can describe this type of situation that we are going to find in the linked data in a given moment. And the idea is to try to discover this type of thing in order to select the engine that we are going to use in a given moment in order to navigate in the graph representation of internet. Okay? Well, we need to select this one is the classical dialectic engine that have been developed, and the idea that we need to switch in one of them according to the sentence that we're going to find in a given moment. Okay, I have finished here. This is a book that is going to be published in Spanish around the semantic mining idea, the technique, not about my work. We can find my work in my web page. You can have the same title of the presentation. You are going to have my presentation in the web page too. But this is a book that talks about the different semantic mining technique, etc., that have finished, but at this moment are in different correction, etc. Okay, thank you very much for your attention, for the time.
Questions or does it
They have anger.
Sure, first question.
Oh, Ernesto, please.
Yes, Jose, about you at the beginning you were talking about this autonomic process, and you have been showing different decision models. In the autonomic process, normally we have phases of observation, diagnosis, and execution of execution. How do you can connect these models in these different phases? I mean, for example, you need to observe, you need to decide which value you need to observe, then you need to identify problem, and you need to find the solution. How do you recommend these?
In our case, the output of, we define each phase is defined for a set of data analysis techniques. For example, we have a specific data analysis technique to monitor, for example, one process. We can
too
have
much data and for upstream to go very fast.
in real time. Yeah, but of course, we can talk about the time, etc. But the idea is that you have one set of data analysis technique that monitor the process. You have another set of data analysis technique that try to interpret the process. This one is going to produce information, data, that is consumed by this one. Okay? There are different ways that we can use that. That means we can share the knowledge database, or maybe the input of this one is going to go directly to the other.
In that phase is more reduction.
Yeah, and that depends on the problem. For example, the real-time constraint that we can have maybe define that the specific information that one that analysis technique that is used to interpret the situation need to have this data in one specific condition. That is very. Remember that when I have talked with the technique to develop the autonomic cycle, there is one phase dedicated to the technological aspect that we need to consider, and in this case, that is one non-functional aspect that we need to consider for the specific problem that we have. We are going to try to attack with this idea. The main point is that in each step, in this phase of the autonomic cycle, the information that produces the set of tasks in each step is used. Yeah, because the next one is very specific for one role in the autonomic cycle. Okay. And this one, for example, one example is at the level of the price of the oil. Maybe we have that analysis technique that try to search in different websites, different places, information about the behavior of the oil price. And that is the problem of this set of data analysis technique. And we have another data analysis technique that the problem is another. This set of data analysis technique use the information of the oil process that has been defined by this one. But it's only one more information, and the way that is made, etc., is not the problem of this set of data analysis technique. That is more or less the idea. Okay.
Okay, are we done? Thank you, Jose.